Hey everyone, it's Nicola here. In this video, I'd like to show you how the RSA crypto system works. The content of this video is going to be a bit more complex compared to my previous ones, but I'll do my best to explain everything to you. If there's anything that's unclear, please let me know in the comments below and I'll try to explain it further. Without further ado, let's get started. RSA is one of the oldest public key crypto systems that is widely used for secure data transmission. Its name comes from the last names of 3 cryptographers that invented it. If you want to learn about asymmetric cryptography, RSA is probably the best crypto system to start with. But what problem does it solve? RSA provides a secure way for 2 people to communicate over an insecure channel. What exactly do we mean by that? In its most basic form, 2 people, usually Alice and Bob, want to send secret messages to each other. However, a villain called Oscar tries to intercept and read their messages. RSA crypto system allows Alice and Bob to speak with each other while making it impossible for Oscar to understand them, even if he could read all of their messages. Alice encrypts the message using some key, then Bob decrypts the message using either the same or a different key depending on the type of the crypto system. There are 3 types of crypto systems that are worth mentioning: secret key crypto system, public key crypto system, and hybrid crypto system. Secret key crypto system is known as symmetric cryptography because Alice and Bob use the same secret key to encrypt and decrypt messages. Symmetric cryptography is usually fast, but the disadvantage is that the secret key must be exchanged over a secure channel ahead of time. For example, Alice and Bob would have to meet in person to exchange the key before they can text each other. Public key crypto system is known as asymmetric cryptography because Alice and Bob use different keys to encrypt and decrypt messages. The key used for encrypting messages is public, which means everyone has access to it. On the other hand, the key used for decrypting messages is private. For example, both Alice and Bob would have different pair of public and private keys. Alice can encrypt messages using Bob's public key that only Bob can decrypt using his private key. If Bob wants to send a message to Alice, he uses Alice's public key, and Alice uses her private key to decrypt those messages. The advantage of asymmetric cryptography is that Alice and Bob don't have to exchange keys ahead of time, which is very useful if they live far from each other. For example, Bob can come up with public and private keys, keep private key to himself, and share the public key with the rest of the world. The downside is that asymmetric cryptography is slow. RSA is an asymmetric crypto system. Apart from securely exchanging messages, RSA is also well suited for digital signatures, but we will talk about them another time. The hybrid crypto system uses both symmetric and asymmetric crypto systems to get the best of both worlds. The idea is to use the asymmetric cryptography to exchange the secret key, then use the symmetric crypto system to exchange messages. As a result, the hybrid crypto system allows Alice and Bob to exchange the secret key even though they haven't met in person, while still getting the speed benefits. We usually say secret key when we refer to the symmetric cryptography, and we use public key and private key when we refer to the keys from the asymmetric cryptography. Before we talk about RSA, I want to cover building blocks from the number theory that the RSA crypto system is based on. We will first introduce Euler's Totient function and Euler's theorem. Then, we will construct the idea in RSA based on this theorem. After that, we'll dive deep into the mathematics of RSA's public and private keys. I will also explain why prime numbers are important and how to find them. And finally, we'll finish this video with some code examples. Let's start with Euler's Totient function. Just in case you don't remember, we say that a number greater than 1 is prime if it can only be divided by 1 and itself. For example, 2, 3, 5, and 7 are prime numbers because they can only be divided by themselves and 1. Also, we say that two numbers a and b are relatively prime or co-prime if their greatest common divisor is 1. For example, 3 and 8 are relatively prime because the greatest common divisor of 3 and 8 is 1. On the other hand, 3 and 9 are not relatively prime because GCD of 3 and 9 is 3. Now that we remember the basics, let's define Euler's Totient function. The Euler's Totient function for a number n counts how many positive integer numbers, up to the number n, are relatively prime to n. This function is written using the Greek letter phi. Can you tell me the value of phi of 9? Let's go over this example together. 1 and 2 are relatively prime to 9 because their greatest common divisor with 9 is 1. Greatest common divisor of 3 and 9 is 3, so 3 is not relatively prime to 9. We do this for all numbers up to 9 and count how many are relatively prime. There are 6 relatively prime numbers with 9, so the phi of 9 is 6. These numbers are 1, 2, 4, 5, and 7, 8. Do you know what numbers are relatively prime with a prime number p? Well, the answer is all except for number p. Therefore, phi of p when p is a prime number is equal to p minus 1. And that's all there is to Euler's Totient function. Now that we know what this function is, we can go ahead and introduce Euler's theorem. Euler's theorem says that if and only if a and n are relatively prime positive integers, and phi of n is Euler's Totient function, then a to the power of phi of n is 1 modulo n. Let's take some time to understand this. The left-right arrow, which stands for if and only if, means if the statement on one side is true, then the statement on the opposite side is true as well, and vice versa. In a nutshell, the left and right statements are equivalent. Let's see an example. If I ask you, what is 5 to the power of 6 modulo 9? Can you answer it using Euler's theorem? Feel free to pause the video here. We already know that phi of 9 is 6. If you pick any number a that is relatively prime to n, then the theorem says that a to the power of 6 is 1 modulo 9. Since 5 is relatively prime to 9, then we conclude that the result is 1. We can verify this by computing 5 to the power of 6, which results in 15,625. Then we can find the remainder when dividing with 9. This gives us a quotient of 1536 and the remainder of 1. We are not going to prove this theorem since our focus is on the RSA cryptosystem, but this is a fundamental idea that we will use to construct it. In every cryptosystem, we would like to have an encryption function that takes a number x and a key and produces a number y. The encryption function is often referred to as the trapdoor function, which means that it's practically impossible to find the number x given only number y. But it's possible to do that if you have the necessary secret information. We refer to x as plain text and to y as ciphertext. The idea for the encryption function in RSA is to compute y by raising x to some power a modulo n. Let's say that we want to encrypt a number 11, and we choose numbers a equals 3 and n equals 200. First, we take 11 to the third, which gives us 1331. Then, after taking the modulo 200, the encryption function produces 131. We would use the same encryption function for any number x. So, how can we get back to the plaintext 11 given the ciphertext 131? We need to reverse the process somehow. The idea for this trick comes from the number theory where, in some cases, it is possible to raise the ciphertext to the power of some number b and take that modulo n to get back the original number. For example, we could raise the number 131 to the power of 27, which gives us this very big number, and after we take that number modulo 200, we will get back 11. With this idea in mind, the decryption function could be y to the power of b modulo n. I think this is amazing, but can we choose such a number b that can reverse the process for any number x? If we want encryption and decryption to work for any number x, we need to show that decrypting the ciphertext always gives us back the plaintext. The key part that we will focus on is x to the power of a times b is congruent with x modulo n. This is where the Euler's theorem comes into play. We know that x to the phi of n is 1 modulo n when greatest common divisor of x and n is 1. Let's multiply each side with x to the phi of n. Since x to the phi of n is 1, we can replace the right-hand side with 1. We now have x to the power of 2 times phi of n. We can repeat this process multiple times, which shows that x to the power of k times phi of n is 1 modulo n for any integer k. But why is this relevant? These two equations look quite similar. The base x and modulo n are the same. The exponent and the right-hand side are different. We can multiply the second equation with x on both sides to make them similar. These two equations tell us that we can decrypt the ciphertext if we can find the solution for a times b equals to k times phi of n plus 1. In our example, we have chosen a to be 3 and n to be 200. We can find phi of 200 by counting how many numbers are relatively prime to 200. You can try to find the answer for yourself, or you can just believe me that phi of 200 is 80. Therefore, if we can find solutions to the equation 3b equals 80k plus 1, then we'll be able to decrypt the ciphertext. How can we do this? A naive approach would be to try every integer number k until we find a solution. For example, for k equals 0, we get 3b equals 1. In this case, b is 1 over 3, and there is no integer b that is a solution here. So let's keep going. For k equals 1, we get 3b equals 81. In this case, b is integer 27, which is the solution, and we can use it in the decryption function. We have already seen that 27 is the solution for our example, and now we know how to compute it. However, trying all integers until we find the one that works is not practical. Fortunately, we can use the extended Euclidean algorithm to efficiently find the solution for equations of the form tx plus zy equals greatest common divisor of t and z. You can notice that our equation looks similar. The only requirement is that the right-hand side is 1. In our example, we can use t equals 3 and z equals 80, which gives us the equation 3x plus 80y equals GCD of 3 and 80, which is 1. Running the extended Euclidean algorithm gives us x equals 27 and y equals minus 1. The solution for x will be the exponent b we are looking for. Notice that the algorithm can only find the solution when GCD of a and phi of n is 1. So this is an additional constraint that we need to be aware of when constructing the RSA cryptosystem. We will cover the extended Euclidean algorithm in another video. Some of you may have noticed that with our choice of n, we won't be able to encrypt every number x and reverse the process correctly. For example, if we encrypt numbers 10 and 20, we will get 0 for ciphertext in both cases. This is because n must be square-free, which means that it's not divisible by a number that is a full square, for example 100. We've covered a lot, so this is a good moment to recap what we've learned so far. The Euler's Totient function for a number n counts how many positive integer numbers, up to the number n, are relatively prime to n. The Euler's theorem says that a to the phi of n is congruent to 1 modulo n when GCD of a and n equals 1. Encryption function in RSA is e of x equals x to the a modulo n, and the decryption function is d of y equals y to the b modulo n. And finally, we can use the extended Euclidean algorithm to solve the equation a times b is congruent to 1 modulo phi of n given a and phi of n. This all looks great, but can we actually use it in practice? In a public key cryptosystem, everyone can encrypt a function, which means that everyone must know numbers a and n. Since b is used for decryption only, we can keep it private. However, if everyone knows n, can't they use the same approach to find the number b? Of course they can. This is why we have to make it infeasible for everyone to calculate b, even though n and a are public. But at the same time, we need to do something clever to make it easy for us to do so. How can we do that? The core problem is that if someone knows phi of n, then they can compute the private key. Therefore, we need to make it infeasible to compute phi of n from the public key. Fortunately, there is another trick that we can use. We know that phi of p equals p minus 1 when p is a prime number. Also, a nice property of the Euler's Totient function is that it is multiplicative. This means that phi of x times y is the same as phi of x times phi of y. For example, we can calculate phi of 40,000 as a product of phi of 200 and phi of 200, which is 6,400. For two primes p and q, phi of p times q equals p minus 1 times q minus 1. If we choose n as a product of two primes, then it would be easy for us to compute the Euler's Totient function. We can keep p and q private so that everyone else would have to go through a more complex process to calculate phi of n. But how hard is it for others to compute phi of n? The quickest way to find Euler's Totient function of a number n is to factorize it, then use a formula to compute phi of n. The most efficient classical algorithm for factoring large numbers is called general number field sieve. We won't go into the details of this algorithm, but it's important to know that if anyone can find factors p and q, then they would break the RSA cryptosystem. However, if we choose very large prime numbers that are thousands of digits long, then it would be very hard for anyone to compute them. Fortunately for RSA, there is no known way to compute phi of n with today's hardware and algorithms in a practical amount of time. This may change in the future with quantum computers, though. Today, factoring algorithms are able to factor RSA modulo having up to hundreds of digits. It is currently recommended that you choose both p and q to be at least 1024-bit primes, meaning the modulus will be at least 2048 bits long. Factoring a number of this size is well beyond the capability of the best factoring algorithms today. However, we should still be careful how we choose p and q. For starters, they should be different and far apart. If they were the same, the attacker could calculate them using square root, which is easy even for large numbers. Also, as mentioned earlier, we wouldn't be able to encrypt and decrypt all numbers if p and q were the same. If p and q are close to each other, the attacker could try dividing the number n with prime numbers starting at square root of n and then go down until they find one that divides n. There is an interesting example in the article from the Scientific American. I'll leave the link in the description. It stated that it would take 1,000,000 years to break a new kind of cipher. The article presented a challenge which was solved 17 years later, in April 1994. The statement referred to how long it would take to run the best factoring algorithm in 1977 on the fastest computer at that time. But computers got faster and better factoring algorithms were found in the meantime. This means that it's difficult to predict the security of a cryptosystem. Okay, now we have enough knowledge to properly define the RSA cryptosystem. So let's do that. Modulo n is chosen as a product of two very large prime numbers, p and q, that are far from each other. Exponent a is chosen at random such that the greatest common divisor of a and phi of n is 1. This is our public exponent. Exponent b is a modular inverse of a modulo phi of n and is computed using the extended Euclidean algorithm. Public key consists of a public exponent a and modulus n and is shared with everyone. On the other hand, private key is kept as a secret and it comprises of b, p, and q. Encryption function raises x to the power of a and returns the result modulo n. Decryption function raises y to the power of b and returns the result modulo n as well. Let's go over a basic example. Suppose Bob chooses p equals 101 and q equals 113. Then modulus n equals 11,413 and phi of n is 100 times 112, which is 11,200. The next step is to choose an exponent a. We can choose any number a as long as the greatest common divisor of a and phi of n is 1. The only prime factors of phi of n are 2, 5, and 7, so a can be any number that is not divisible by 2, 5, or 7. Let's say that Bob chooses a equals 3,533. In practice, Bob will not factor phi of n. Instead, he will verify that the greatest common divisor of phi of n and a is 1. You will see what I mean when we get to the code example later in the video. Next, Bob will compute the private exponent b using the extended Euclidean algorithm and get number 6,597. Finally, Bob publishes n and a as a public key and keeps the other numbers secret. Now let's say that Alice wants to encrypt the plain text 4923 and send it to Bob. She computes the plain text to the power of 3,533, then takes that result modulo 11,413 and gets a number 3,507, which is the ciphertext that she sends to Bob. When Bob receives the ciphertext, he uses his secret decryption exponent to reverse the process. Now you know how RSA works, but there are a couple of things that are not obvious. One is how to find very large prime numbers, and can we efficiently implement encryption and decryption functions when dealing with large numbers? Let's look into these things. Let's see how to find two large prime numbers first. We can choose a large number at random, then check if it's prime. If the number is prime, we keep it. Otherwise, we repeat the process until we find the prime number. We can use the same algorithm to find the second prime number. It's simple, right? Well, that sounds easy, but how do we check if a given number is prime? There are many algorithms that test if a number is prime or not. The most commonly used one is called Miller-Rabin primality test. This is a probabilistic algorithm which determines whether a given number is likely to be prime. The longer the algorithm runs, the higher probability that the answer is correct. I will cover the Miller-Rabin primality test in another video. Okay, so we know how to test whether a number is prime or not, but how long would it take to choose one at random? Good news is that there are infinitely many prime numbers, and mathematicians have worked out the probability of a number being prime. Based on the prime number theorem, the probability that a random number not greater than n is prime is very close to 1 over log n. This means that for a number that is 1024 bits long, the chance of it being prime is around 1 in 1,000. Therefore, it would take about 1,000 attempts to find a prime number for RSA on average. Now let's see if we can efficiently implement encryption and decryption functions. Assuming that we have public and private keys, how long would it take to run encryption and decryption functions? We can use elementary school arithmetics to find the upper bound on the amount of time to perform various operations of two large prime numbers. Let's say that we have two numbers x and y with k and l bits respectively. We can assume that k is greater than or equal to l for simplicity. Addition can be computed in O of k. Subtraction has the same time complexity as addition. Multiplication is a bit more complex and can be computed in O of k times L. Division has the same time complexity as multiplication. And finally, GCD of x and y can be computed in O of number of GCD iterations times number of divisions. And this is O of k to the third because the GCD algorithm performs a division in each iteration, which is O of k times L, or we can simplify it to O of k squared, and it runs in O of k iterations. In fact, it can be shown that the complexity is actually O of k squared because the numbers become smaller in later iterations of Euclidean algorithm. Let's also briefly mention modular arithmetics. Modular addition can be computed in O of k, assuming n also has up to k bits. Modular subtraction has the same complexity as modular addition. Modular product can be computed in O of k squared. Instead of modular division, we often need to compute modular inverse, which can be done in O of k to the third. This is done using the extended Euclidean algorithm. And finally, computing x to the power of v modulo n can be done in O of log of v times k squared. Most of these are easy to prove. The first three can be done by doing an integer operation and then performing a single reduction modulo n. The multiplicative inverse algorithm with large numbers is no different compared to small numbers. We just need to account for the time complexity of large number operations. Finally, computing modular exponent, which both encryption and decryption operations need, can be done using E modular multiplications. However, this would be very slow if E is large, which it almost certainly will be in practice. Instead, we can use square and multiply algorithm where this can be computed in O of log of E iterations. The idea is that for an even number E, we can reduce the problem to computing the power of E over 2, then computing the square of that number. This means we can replace half of the iterations with a single multiplication. When E is an odd number, we can reduce the problem to the previous one with a single multiplication. This means that we can compute the encryption and decryption functions in O of k to the third, assuming number E also has k bits. In practice, there are tricks that can improve performance of these functions even further using Chinese remainder theorem, but this is out of scope for this video. Now let's see a step-by-step example that shows how RSA works in practice. We will write some code to generate private and public keys, then test if we can encrypt and decrypt some values. Before we do that, I want to highlight that you should never implement RSA yourself unless you're an expert. Even then, you should probably use an existing library because it's very hard to cover all security loopholes. Note that the following code is just for learning purposes and it doesn't fully cover all the security aspects. We will write Python code to generate private and public keys, then assert that we can encrypt and decrypt any value. Our first step is to generate public and private keys. To do that, we need a way to generate a random number of a given length, and a function that tests if the number is prime. I'm going to use two libraries to do this, as the goal of this video is to understand only the aspects of RSA. Next, let's write a function to generate a large prime number. We will do that by generating a large random number, check if it's prime, and if not, keep doing that. Okay, we are now ready to generate two large prime numbers, p and q. We want these two numbers to be far apart as well, so we will keep generating them until they are far from each other. Now we can generate p and q by calling the generate prime factors function. Since I can't fit a 2040-bit number on the screen, I'm going to use just 128-bit factors. If we print these numbers, we get some large prime numbers p and q and their product n. Next step is to generate a public exponent. We will keep generating a random number a until a is between 1 and phi of n, and the GCD of a and phi of n is 1. I'm using eGCD library that implements the extended Euclidean algorithm for us. Note that we only care about the GCD here, so we're ignoring the other return values. Now that we have the public exponent, we can use the extended Euclidean algorithm to compute the private exponent. Before we can do that, we need to calculate phi of n, and fortunately for us, that's easy. Let's run these two functions to generate public and private exponents and print the public and private keys. All that's left is to test if we can encrypt an arbitrary number, then decrypt it. Before we can implement encryption and decryption functions, we need a function to calculate modular exponents. We can implement this recursively using the square and multiply algorithm, which we explained earlier in this video. The implementation of encryption and decryption functions now is trivial. Let's test this by encrypting an arbitrary number. I've chosen x equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. And we're done. This works indeed. You can find the full source code of this example in the description below. I hope you've learned something new today. This video only covers the basics of RSA, but there is a lot more detail and subtleties around security that I didn't mention. RSA Cryptosystem is probably the simplest asymmetric cryptosystem to learn, but is still widely used. However, people are slowly moving towards the elliptic curves cryptography because it provides better security guarantees for the same length keys. Also, don't forget to hit the like button and subscribe to this channel. It would mean a lot to me. And I'll see you in the next video.